In order to demonstrate this, I first of all have to demonstrate an electroscope. Now, a simple electroscope just has pieces of foil that are hanging. And when I put a charge on the electroscope, some of that charge spreads out to the foil, and then the foil is repelled from each other, and you can detect the presence of the charge. My electroscope is a little bit more complicated. It's made up of this metal ball here that's connected by metal to this vertical bar. Now that vertical bar contains a second little bar that's free to rotate. Now this outer metal is just structural support. It's not part of the device. And you can see that it's not connected to the metal bar or the metal post because there's plexiglass top and bottom here insulating it from this circular metal. Now, if I take a rubber rod and I charge it up with a simulated rabbit fur, first of all, remember that this is an insulator. This is not a conductor. And so when I charge this up by putting extra electrons on it, the electrons are stuck where I put them. And so if I just touch the metal ball with this, all I do is transfer those electrons that were right at the location where I touched the ball. And you see that it didn't have very much effect. If I want to transfer more charge to that electroscope, I've got to scrape it off the rod like it were peanut butter, okay? And that gives all the electrons a chance to jump ship. And now you see that the vertical rod and the rod that's free to rotate are repelling each other, and so I get something that indicates that there's charge. Okay, has everyone had a chance to see that? Okay. Now to neutralize this, I just touch it to a very large conductor. Well, I'm a very large conductor, and so I neutralize it. Now, what we're going to do is we're going to start with a neutral can, and we're going to dump a bunch of electrons in this can with this Wimshurst machine. Now the Wimshurst machine is a way of separating negative charge from positive charge through a process called induction that we'll talk about towards the end of the semester. But suffice it to say that now I just collect electrons here and I'm missing electrons over here, and so this rod would be negative, this rod would be positive. And if I turn the crank and collect the charge, I can build up enough charge that it actually jumps the gap. Now, Friday we'll start talking about voltage. But your gut tells you that voltage is all about fear. How afraid should I be of that? Okay? And it turns out that in order to jump a 1 centimeter gap of air, you need 30,000 volts. Okay? So we're generating a fair amount of voltage here. Now, what I'm going to do is I'm going to start with this can being neutral. I know it's neutral because I'm touching it. I can show it's neutral by taking this wand and nothing. Okay? So you keep her the wand. Okay? Now, I'm going to take this chain and hang it on the negative side and put the negative side away from the positive side so it can't jump a spark. And I'm going to turn the crank, generating electrons and dumping them into the inside of that can. And I'm going to dump a whole lot of electrons because I'm generous and they're free. So we'll just fill that can right up. Okay? Now, I'm going to use this wooden stick to take the chain and put it off there. Now, if I take my wand and touch it all around on the inside, and come over here, I get nothing. And there's a little bump from the collision, but nothing. Where'd the electrons go? On the outside. If I touch the outside, there you go. Yeah, that's the response I was looking for. Okay. And this time it stays deflected. Okay, so all the charge goes to the outside. This was first demonstrated by Michael Faraday, so it's called the Faraday bucket. Now, we can use that Faraday bucket idea to talk about what this gentleman brought up with lightning. If we look at lightning, there's some lightning. That lightning was on the day, the actual moment, I think, that Pope Francis was chosen. Not a relative. Not a relative. There's some lightning in Dubai. How many of you have been to the Boston Museum of Science? They have the most marvelous Van de Graaff generators. In truth, only one of these is a Van de Graaff generator, and the second is just a facade. But in one of these, I'm not sure which one it is, there's a giant rubber band that rolls up and down. And just like our little Van de Graaff, we spray charge on it with a metal comb, and we take the charge off at the top. And they build up huge charge distributions up there. Now, what they have here is a graduate student, because they're expendable, in a metal bird cage. And what they do is they charge up the Van de Graaff, and then they lift up the bird cage until they get lightning. And the grad student demonstrates that the charge stays on the outside of the cage by putting his or her hand right on the metal bars where the lightning is striking, on the inside. Now, we used to take our kids there all the time, and there was one grad student who was more brave than the rest. And what he would do is he would put his tongue right on that bar on the inside. And I tell my kids, that's my hero. That's who you want to grow up to be. That's who you want to be. Now, when we're in a lightning storm and we're away from our house, the best thing we can do is crawl in a metal can, or better yet, crawl into your car. And in your car, you are protected from that lightning. Why?
Electrons like the outside.
What's that?
Electrons like the outside.
Electrons like the outside. Exactly right. Now, the more common answer that you hear is because of the rubber tires. And the rubber tires will protect you from the lightning if your rubber tires are 1 mile thick. I don't have tires like that. It turns out that it's the Faraday cage, the metal cage around you, that protects you. If you're in a Corvette, you're toast.